Good morning, good afternoon, good evening, wherever you may be. It is with great pleasure that Catherine and myself welcome you today for our first event organized through the Plugin Abandonment Technical Section of SPE. It'll be a series of webinars that we hope to deliver this year. There'll be another one in a week time, and then gradually bring some of the interesting conversations to a wider audience, continuing in 2025. So without any further ado, I'm going to bring the speakers for the day onto the stage, and then we'll start the introductions. If you want to say a few words, Catherine, feel free.
Yeah, so just as to give us a background, in the last decade, Norwegian institutions have joined efforts to move forward with the advance of P&A technologies, including diagnosis of barriers, qualification, placement of barriers, and also materials. Today, we would like to share a little bit of the research in materials that have been brought in Norway and include cementitious materials, but also new or novel materials as bismuth. To start with this discussion, we have three panelists today. We will have Marcello Giaculli that will start with the presentation. He's a postdoctoral researcher at NTNU in Norway. He has working with research in well engineering, focusing on well integrity and P&A. And his recent focus have been in bismuth alloys. He also has experience in mechanical and ocean engineer applications within petroleum engineering, including structural analysis, vibration, vessel dynamics, and reliability. Marcello holds a degree in mechanical engineering and both master and PhD in petroleum engineering from the University of Campinas in Brazil. So the floor is yours, Marcello.
I'll introduce Nina first, and then you'll introduce Martin if we follow. So Nina, our second guest speaker for today, is Nina Ringoon. She's currently Chief Engineer for Drilling and Well Technology in Halftiel, Norway, a position she's held since February 2017. Before this, she had 26 years of industry experience covering the full well life cycle with Phillips Petroleum, ConocoPhillips, Centrica Energy, Talisman Energy, and Suncor. In her role at Halftiel, Nina is leading multiple tasks involving Norwegian continental shelf operators and service providers, including acting as a focal point between service providers and research institutions for qualification of new technology and solutions for P&A. Nina holds an MSc in offshore technology and an MBA, both from the University of Stavanger. And then to our third speaker.
Okay, and our last speaker of the day is Martin Strome. He is the Chief Engineer and Discipline Lead for P&A in Aker BP in Norway. After a long career on various positions with Amoco, Statoil, Saga, and Phillips Petroleum, before he joined Aker BP in 2005. In his roles, Martin covered engineering and supervisory positions on both onshore and offshore operations. He holds an engineering degree from Norway and civil engineering in 1981 and West Virginia University in petroleum engineering in 1984. He is also a guest lecturer for P&A at the University of Stavanger.
Very good. Thank you, Catherine. So Marcello would go first, Nina will then follow, and then Martin will finish with practical case of application in Norway, and then we'll have a panel discussion. So feel free to include questions in the comments, and we'll select a few after the fact. So see you in a bit. Marcello, I'll put you on the stage.
Okay, thank you very much for the introduction. It's a pleasure to be here and talk about our research being carried out here at NTNU. So as per the introduction, I'm a postdoctoral fellow at NTNU, but in particular, I'm a part of a project called SPE, which is a research consortium involving several research institutions here in Norway, including universities and other institutes. And then I'm going to talk about the research we have been carrying out regarding bismuth alloys here at NTNU. So just a quick talk about what's SWIPA. So it's funded by the Research Council of Norway, but it also has industry partners which fund the consortium partially. And the focus has been on the performance of well barriers. So then in this sense, we are inside one of the work packages, which is focused on developing new well barrier materials and testing then for potential P&A applications. So then there are other materials being tested aside from bismuth, but our team here at NTNU has been focused on it. So you can check our latest developments in our annual reports. And in particular, we had the pleasure to be on the cover for the latest one from 2023. And you can see more about the whole work of the consortium there. So just to give a quick context for those that might not be familiar with the problem. So for cement plugs applied to P&A, we can see that there are some potential leak paths, not only on the cement plug itself, but also other leak paths along the cross-section. And in particular, the bismuth plugs aim to solve this two here. So you might have a loss of plug integrity. So let's say that you have some channels through your cement plug. This can be solved by a bismuth plug due to the fact that it's impermeable. So then, of course, being a metal plug compared to a porous material like cement has this advantage of being impermeable. But also it could provide better sealability in terms of the annuli that it can be formed between the plug and the pipe inner wall. So since bismuth alloys, they expand after they solidify, they can help close this annuli and thus achieve better sealability between plug and pipe. So here for our research approach, we have done lab tests and numerical simulations and working together on these two fronts. So then we could compare results and also improve our own lab tests methods. So here on the left side, you can see a sample of a bismuth tin eutectic alloy. So then we just take this and we pour the liquid alloy into one of these pipes. And then after it solidifies, it forms this nice plug inside the pipe. And then we take this for testing. And in parallel, we built the same kind of geometry on the commercial software for finite element analysis. And then we carry out the same lab tests in the software and try to compare the results so we can calibrate our models. So we have carried out a lot of lab tests here, a lot of different lab tests. But one of the things that probably took a lot of our time initially was learning how to set up this plug in an efficient way. So then we knew that when we took it to testing, we could ensure that the results that we were getting afterwards, that they were meaningful. So then, as you can see here on the lower right side, you can see this is a small bubble on the plug surface. So this is something that we learned on how to eliminate when setting the plug. You can see here on the lower left, the steel liquid alloy. And then there you can see it's being poured inside the pipe. So then we just went with this setup, and then based with this setup, we were able to perform several different tests. So the main tests we carried out in the last 2 years have been hydraulic push-out tests. So we apply a hydraulic pressure in the upper surface, and we see how much pressure it can withstand before the plug is displaced. So by being displaced, it could mean simply that it lost its sealability capacity. So you see, for example, a drop in pressure being measured, which means that it's probably some leakage around the plug. Then it means the plug has shifted from position, and then you can no longer trust its capability of sealing the well. So then we carried out for that setup from the last slide, and then we tested for several different temperatures. So for this particular alloy, the eutectic bismuth tin, the melting point is 138. So then we tested very close to the melting point and also up to like environmental temperature to see what effect the temperatures would have on it. Another test that we did at the very beginning was testing like leakage through it using nitrogen. So it compared cement plugs with bismuth plugs to see who had the lesser leakage rates. And then we saw that a bismuth was very competent in shutting down the leakage in this case. Compared to cement, but that was like a very early test that we did when we were learning about the whole setup and the whole problem. Another thing that we tried was increasing the pipe inner diameter. So you can see here on the picture in the middle that we cut a section of the pipe thickness. So we increase the inner diameter, and this creates kind of a seat, as you can see here on the diagram on the right as well, where once the plug solidifies, it improves its contact area with the pipe. And then we saw that when we tried to push this out, we actually ruptured the pipe because it was very competent. So then we said, okay, maybe we need a better pipe for this kind of setup, because we weren't even able to push out the plug in this case. Another thing that we did was testing the effect of the bismuth expansion on the annulus cement. So this was done in collaboration with SINTEF with a CT scan. So then we have here a pipe and the cement behind it. And then we set a plug inside the pipe, and due to the plug expansion, you expect the pipe to deform as well. And this can cause some deformation on the cement as well. But depending if the cement has cracks before, you could close these cracks because of this deformation. Or if it's not cracked, then you might cause the cracks yourself. So we were not sure what would happen in that case. And based on what you did, unfortunately, we were not really able to give like clear results because from the images, as you can see here, it was not very clear what kind of contribution the bismuth plug had. So on the left side, you have the initial CT scan before setting the plug. You can see some black spots, which are cracks. Then after you place the bismuth plug and you try to do the CT scan, it's very difficult because of the metal core. It kind of obfuscates the rest of the cement. So you don't really see a lot of contrast here. So I said, okay, let's try to remove the plug and see the after effects. Then you can still see that some of the cracks were there, but you can see that some of them disappeared. But we said, okay, we're not entirely sure what's happening here, if these cracks were really closed, or maybe the CT scan is not the best approach here. But this is something that definitely deserves more investigation. Another test that we did was what we call the bubble rig test. So we set a plug while we are having a gas leakage, and then we see the capability of the bismuth plug to solidify and seal an active gas leak. So then we have this nice video. I hope it's playing there on the presentation, but you can see a lot of bubbles coming from the plug, and you see that over time they will stop. So the resolution is not very good, but you can see the bubbles on top. And then after a while, the plug will shut down the bubbles completely as the alloy finishes solidifying. So then it said, okay, then it means the plug can shut down a gas leakage. However, when we cut the plug and see the cross section, we see that there are a lot of holes here. So I said, okay, although we are able to shut down the gas leakage, maybe this plug won't be able to withstand the hydraulic pressure when we apply it. So that's when we concluded that maybe in the case of an active gas leak, you might want to set a plug first to shut down the leakage, and then you could have an extra plug, an extra segment of plug up above this one, where you would be able to create a more competent plug since you don't have the leakage anymore. So then these are at least some initial discussions that we had. Another thing that we tried was checking the effect of pipe roughness. So we realized that there is a balance here between not having a surface that is too polished, because you want some friction, because essentially that's what's holding the plug in place. It's purely a mechanical effect, so it's the friction between the two metals that is keeping the plug in place. But you don't want also to have some type of contaminants. So if you set this in a mud environment, you might get your mud inside the plug. So this might cause some problems when the plug solidifies and contaminates, and it might not have all the properties that you want. So then there is a fine balance between cleaning the pipe inner wall, but also not polishing it too much, because otherwise you lose the friction. And another study that we also carry out was regarding microscope analysis for the microstructure. So it's not really my field here, but we have done some tests with the plugs after they solidified, and then we could identify the microstructures. And of course, by seeing like finer grains, you are expecting better properties. When you see this coarse grains, these crystals of bismuth material within the tin, then you expect this to have not as good properties as the other case. But then that's a separate work here that you could check in our publications. And in parallel with that, we have been carrying out the numerical modeling, and based on the lab observations and also what we knew about the physics, we came up with the conclusion that this problem could be explained by three combined phenomena. So we have the expansion that happens because of the bismuth alloy. It's a very unique quality. And then we know that the expansion doesn't happen instantaneously, but over time. So the manufacturer provides how much the alloy is expanding over time. So you have like a nice curve that you can work with. And we know that this, at some point, of course, the alloy will stop expanding. And in parallel with this effect, you have creep effects. So it becomes more relevant at higher temperatures, closer to the melting point. And this is going to, of course, counterbalance the expansion effect. So we noticed that if you are operating at temperatures very close to the melting point, creep is so much that you cannot keep the plug in place. It won't resist any pressure. So there is some threshold temperature, which is the maximum operating temperature you could have for that particular alloy. And finally, we have aging effects, because due to the extended periods of time and the high loads, high temperatures, you expect elastic properties to change. But there is little investigation in the literature yet about this. So again, there is no chemical bonding. It's a combination of the expansion plus friction between plug and pipe, providing the resistance, the strength here against hydraulic pressure. And we know that the surface roughness is a key factor for this. So like establishing a clean environment for setting the plug is very important, but also not polishing the casing inner wall too much. And then we take this to perform numerical shout tests on ANSYS. And we have proposed a model that combines the three phenomena that were described here. So from the lab results, we saw for the particular eutectic bismuth tin alloy that you have a threshold temperature at this temperature of 60 degrees. So if you think that the melting point is 138, you could apply this alloy up to 60 degrees of bottom hole temperature, or if you want to set as an environmental plug, whatever temperature you have there, which of course probably less than 60 degrees. But if you want to go deeper downhole, then you need to make sure that this alloy, that the maximum operating temperature for this alloy doesn't, the bottom hole temperature doesn't surpass the maximum operating temperature for this alloy. You can see an increasing trend for temperatures lower than 60 degrees over time. So it means as the alloy progresses over time, it will retain its capability of resisting applied pressure. But for temperatures higher than the threshold, as you get closer to the melting point, then the performance degrades over time. And of course, that's not what you want. And then when we try to compare this with the numerical results, we realize that we don't have enough data to capture this kind of behavior yet. So we need more tests regarding the creep behavior to be sure that we can fully characterize the alloys in the software. So as remaining challenges for our research, of course, we came up with what's a very fundamental claim, but good input data is necessary for modeling success, of course. But the problem here in this particular application is that you have a large variability of input data in the literature, especially for creep. So there are like several studies looking at the same alloy, providing completely different models and parameters. So then this needs better testing. And in this case, we put that as a recommendation that those involved obtain more alloy properties, especially for the creep behavior, because that's kind of what defines the maximum operating temperature we will be able to put our plug on. We still don't know much about the steel bismuth friction coefficient, so that's another thing that needs to be investigated. We still don't know much about the effect of the bismuth expansion on tubular and annulus cement, so it's something we wish to investigate further. Creep parameters also change due to aging effects, so those effects that I described, they are also coupled on this, so that could lead to like further modeling complications. And finally, in terms of the companies that are working with bismuth alloys, we can expect them to have this portfolio of bismuth alloys with different maximum operating temperatures. And finding this temperature is mandatory for them to ensure that the bismuth plug is suitable for their downhole environment. So we made several publications that we attended many conferences. You could find this based on our names from the SPE research group. And I also made some journal articles, but you are more than welcome to reach out to me, and I can, of course, share this with who is interested. And I also wrote about the technology at blogs, and we also had a similar webinar for the SPE Brazil section, where I went into more details about the technology, so you could also check that. It's also in English, so you could also check on that. Thank you very much.
Thank you, Marcelo. Excellent presentation, right on time. So we had one question from the audience. We initially thought that we would take the Q&A at the end for all participants to be on board at the same time. If we're okay with that, I'll just move to the next speaker and introduce, and put Nina back on the stage. Thank you, Marcelo. Nina, the floor is yours. I'll theme up your presentation. To you, thank you, on the regulatory requirements of testing of alternative barrier material. Thank you.
Mm-hmm. Okay, thank you very much. So first of all, I wanted to show a little animation or video, but it looks like it's not working here. But we are the previous Petroleum Safety Authority in Norway. Today we are known as the Norwegian Ocean Industry Authority. In Norwegian, we are named HAVTIL or Havindustritilsynet. We have been a safety regulator on the Norwegian continental shelf since 1973, and we have the regulatory responsibility for safety, working environment, emergency preparedness, and also recently security in Norway's ocean industry. And we are subordinate to the Ministry of Energy. When it comes to the topic of the workshop, also this webinar today, it's all about new as well barrier materials or use of bismuth alloy. And I guess what we have ahead of us is this upcoming wave of P&A operations, and on the Norwegian continental shelf we have more than 2,000 wells at the moment, and they are expected to be permanent plugged and abandoned from now on towards 2050 or 2070. And the question is, are we actually ready? And when I ask are we ready, I mean kind of both with respect to ensuring that these wells are permanent plugged in a safe and robust manner, but also in a more cost-efficient way, since we all know that there is no income in the last phase of a well's lifetime, which includes permanent plugging. As you can see here, there is also HAVTIL have got the responsibility for the ongoing petroleum operations offshore and onshore of the Norwegian continental shelf. and there were approximately 2,247 wells in January 2024. We have also got new areas of responsibility supporting our Parliament's ambitious climate goals, but I won't go into details there. When it comes to as a bismuth alloy or qualification of new well barrier materials, so we normally reference our facility regulation section 9. The facility regulation section 9 deals with how we facilitate implementation of new technology. These regulatory requirements are functional requirements, which means that we state what to be achieved, but not how. In the facility regulation, we deal with qualification of both new technology, new methods, and new well barrier materials, amongst others. And we state quite clearly that there shall be criteria for a qualification process, and also criteria for the development, testing, and use of the new technology or the new well barrier material. That includes that the technology or methods shall be adapted to already accepted solutions, which means also based on verification methods or best available practice in the industry, like NORSUC DO10 for establishing well barriers. And we also reference that the qualification of testing shall demonstrate that the applicable requirements in the regulations, for example, with respect to well barriers and to verification of well barriers, can be fulfilled. And it also includes investigation and obtaining objective proof that the needs for specific intended use are covered. And that means also establishing a failure mode and effect criticality analysis, like we referenced in our guidance level with reference to DNV RP 8203 and the Oil and Gas UK guideline for use of barrier materials. So that are the regulatory requirements and the kind of high level goals with respect to qualification of new technology and best available technology, one can say. When it comes to what the facility regulation actually states, it's all about establishing a TRL process in your management steering system. And a TRL process or level is a type of measurement system that is used to assess the maturity level of a kind of qualification or development of that qualification of a particular technology. In Halftil, we don't have any specific requirements for which TRL measurement system to be used. But as you can see here on this slide, we reference both the NASA process and the API 17N process. And we are normally interested when the vendor or the kind of well barrier material is reaching TRL level 4 or TRL level 7, which could also be level 5 and 9 in the NASA measurement system. When it comes to use of bismuth alloy on the Norwegian continental shelf or as a well barrier element, we have a limited experience, but there are several vendors and several operators that are working towards qualification, and some have also have already qualified bismuth for low temperature and low pressure. In 2023, we did a knowledge acquisition study where we asked the two operators and several of the vendors that work to qualify and that have qualified bismuth alloy to provide information with respect to their qualification process and their technology and deployment system. So both Aker BP, Total Energies, Bissen, Interval, Isolate 8 and Wallström participated, in addition to SWIPA, a SINTEF consortium, and Norse, NTNU, IFE, and UES has also contributed. So you can read more about this report on our webpage. In the report, you will see also that there are 3 distinct technologies for deployment of bismuth alloy ongoing today, also at least that was the case back in 2023. It's bismuth alloy melted by thermite in a heated reaction downhole, or it's bismuth alloy melted by an electric heater, also kind of electric line, in a more controlled manner. And then we also have a solution where bismuth alloy is melted or generated also through a thermite reaction that also melts the casing tubing downhole at the position of the well barrier of the element. Then to talk a little bit more about the experience we have with respect to bismuth alloy so forth. Also, what is the current requirements? The current requirements for well barriers are kind of detailed out in NORSOC DO10, and as you might see to the right here, I've just added a sketch of a typical permanent P&A operation, or a permanent P&A well, where you have the primary barrier towards the reservoir, the secondary barrier, and then you have the open hole to surface barrier or open hole to surface plug. And on the Norwegian continental shelf so far, there is only one operator that has used bismuth alloy for permanent plugging, and that is for the last plug, also the open hole to surface barrier, and for some other kind of shallow barriers in the same area. Today, the requirements for a typical primary and secondary barrier is spelled out in NORSOC DO10, table 15, 22, or 24. And then if you're using other kind of well barrier materials than cement, there are, in addition, some compensating measures in place for those well barriers. And they are mainly kind of saying that then you need to do a proper risk assessment. You have to look at the kind of potential fractures and the integrity at the depth of the placement of the bismuth or the alternative material. So to ensure that there are no potential for leaks. Because also the big kind of issue or the challenge with the bismuth compared to a cement plug is, as you can see here on the second bulk, is that the cross-section length of the molten bismuth metal plug is much shorter than a cement plug. It's normally planned for 2 meters of bismuth alloy compared to today's best practice that include a 50-meter cross-sectional cement plug. So given that information, it will be very important to ensure that also where you place that shorter barrier length, that you have risk assessed and ensured that you have integrity and no potential of leaks in that area. And that is actually kind of, there are some guidance in the industry standard NORSOC DO10 saying that pay attention to risk assessment of possible leak paths outside the well barrier element, and also make sure that the selected plugging material is verified and documented for the given pressure and temperature, and also degradation of casing and this kind of expansion and creep need to be considered. Then I've just tried to summarize a little with respect to some of the threats when it comes to bismuth alloy. And when I'm saying threats, I'm just referencing the qualification process. And also some of the points that Marcelo mentioned. You need to look into this expansion of bismuth alloy in a kind of clean casing or clean environment. Also, there are some radial effects, and if it's going to be used as a permanent barrier, it needs to be qualified for eternity or perpetuity. In NORSIC DO10, there are also some guidelines in Table 55 that deals with alternative well barrier materials, but as an operator, and if you have qualified Bison as a well barrier element, it is also important to state that there is a requirement to develop a separate EAC, also well barrier element acceptance criteria table, and for that specific well barrier element. And as mentioned, on the Norwegian continental shelf, it's only qualified for low temperature and low pressure so far. So that was all for me, and I just want to say that collaboration with other authorities and industry partners is key for us in Halftil, and we would also encourage the industry to collaborate with respect to development of both new technology and new solutions, and also new well barrier materials for plugging and abandonment going forward. Then you can visit our website and look at this Bismuth report and our animation of permanent plugging. So thank you very much.
Thank you, Nina. And I think so it's a clear invite for collaboration and sharing of experience and learnings. And this will be the topic of our next chat, the next webinar next week. And I think if people want to see the initial movie, which you were quite keen on showing, Nina, I think it is available on your webpage, right?
That's right. Thank you.
We will have the questions at the end, but I see some people is asking about the availability of the material after today's presentation. So this will be available online in the YouTube link, but also and can be consulted any moment, the presentation of Nina and the links.
Yes, so I think last time we tried to make the attachments available through LinkedIn. I faced some difficulties, but Tim, if you want to get in touch later after the call, I'll be happy to share the presentation material. Very good. And on to Martin for the last presentation. And Martin's going to talk about practical application cases in Norway. And then at the end, we've had a number of questions, as Catherine was saying, and we'll dispatch the questions in a round table format and a bit of a dialogue between the various speakers. So the floor is yours, Martin. Thank you.
Thank you, Pierre. Pierre, I lost one of my screens actually during Marcelo's presentation. So the only thing I can see is actually my own presentation.
It's perfect. It's perfect. So
right.
we can see you, but you're showing your presentation. So things are moving quite well.
Okay. All right. Thank you.
Thank you.
What I am going to talk about today is basically the Bismuth plug that we have used, the Bismuth plug experience that we have from Valhall DP and the HOD P&A projects. And what I want to show you is why we did this. I want to go through a little bit of the qualification that we did, including the offshore test, and how we verified that we indeed could use this material. And at the end, I want to show you how we actually install them. So if I go to the next slide, The next slide is basically showing the field position in the North Sea. As you can see here, we have the Valhall field and the Hod field right there in the intersection between basically all 5 nations: UK, Norway, Denmark, Germany, and Holland. So this is the physical position of where we have installed the plugs, the Bismuth plugs. So here you can see how why we had a need for it. We don't only have a reservoir, we actually have 5 zones above the reservoir, between the reservoir and the seabed, that has collected hydrocarbons over the geologic time. There is a slight water drive in this reservoir, in the Valhall reservoir, and that actually caused higher pressure than the caprock could bear. So the caprock actually broke up during geologic time, and hydrocarbons moved upwards. When we were going to plug this platform that you see the yellow arrow pointing towards, we found out that the annulus between this 20-inch surface casing and the 30-inch conductor actually was seeping biogenic gas as well. And that's why I'm showing you this, this graph on the right-hand side, where green is actually a fully competent barrier quality on all the annuli. But as you can see, it gets worse as we go towards the right. And in most all of these annuli, either the A annulus, B annulus, C annulus, or D annulus, there was some sort of a leakage. So we actually ended up with the fact that we really need to put a material in that could stop even the D annulus, which is not normal to put any material in, except from when you put the surface casing in place, you cement it, and that's about it. But we had a need because we had a leak there. So the sketch to the right actually shows all sorts of leak paths that Marcelo actually showed on one of his first slides. We have actually found out that cement does indeed leak. What you see on the left-hand side, well, on the right-hand side, all the yellow arrows point towards some sort of a leak path that is potential leak paths. And what I want to show you is actually a small video that shows that cement indeed leaks. What you see here are 2 casings and annulus cement in between. It's 95H casing with 13 3/8 casing on the outside. And you can see that this was actually cut and pulled to surface, and you can see how the gas actually empties itself from the pore system in the cement. So cement isn't necessarily sealing all the time. Depends on, of course, how it's done and how lucky we are with the cement job. Cracks could occur also, and whether this is caused by cracks or I don't know, and I can only speculate, but we can definitely see that cement can leak. So I'm not going to go through this. Marcelo has talked about that. It has to do with the bismuth material and how it actually expands, and the viscosity, like water, is really important because it fills out all the small cracks, and we know that water can go anywhere it wants, more or less. So we decided to try bismuth, but before we tried that out, we needed to have a test program. So we went to Houston and ganged up with Bismuth at that time. Bismuth was still there, and we wanted to make a large bismuth plug. This was larger than any bismuth plug they had made before, so we needed to test that out. And we were going to have it shallow, as Nina mentioned. It's qualified for shallow water and shallow temperatures, and well, low pressure. And we tested it towards 200 psi first, and then 500 psi with gas from top and below. And 500 psi was actually about 5 times as much as we needed to hold back the hydrostatic pressure that is found below where we set the plugs. So we made a plug that you can see. A couple of our engineers actually went over there and many times to test out this material. And we made a plug that could be installed in a 13 3/8 by 20 inch annulus. So this is the plug that we made, and I want to show you a little bit about how we actually installed it for testing. And this was going to be sitting there for about 2 years. We installed this in 2018, and we're going to recover it in 2020. So what we did was that we perforated the zone where we knew we had gas to allow gas from coming into this blue brine area below the plug. We installed a bridge plug with gauges underneath, and this bridge plug had actually holes in it. So we should allow the gas to get through the bridge plug, but we needed something to hold gauges. That's why the bridge plug is there. And then we had sand on top of that again, sand enough to let the gas going through up underneath the bismuth plug, which was set in a section milled area where we section milled away the 9 5/8 casing and the 13 3/8 cement, the annulus here. And we had actually also then allowed cement or allowed gas from coming up this annulus and up underneath the same bismuth plug. So we had 2 potential sources of cement. I only showed this one to show that we had milled a section window, which is not easy to see where the red bismuth plug is. So we went through the TRL levels and we installed, I'm not going to talk more about that, it's already mentioned, but we installed, we tested the plug, which was a TRL 5 job for us. We installed the plug offshore in 2018, which was the TRL 6, and then we drilled it out and did the test in 2020 after we had actually seen whether it leaked or not. So during this 2-year period, we filmed it downhole and on surface, and we didn't see any bubbles coming to surface. So what we did was that we designed a mill to mill out the bismuth plug. Unfortunately, when we got back all the way through the bismuth plug and we're going to recover this bridge plug, the casing had shifted. So we really didn't get this bridge plug back through this window because there was a shift of 3 inches. And you can actually see that on this mill here, that you can see that some of the teeth is actually gone on the mill. Here is a fresh mill down on the bottom here. But on top, you can see that the outer part is gone, and that's where it has actually rotated on the top of the stump. When we got through this, when we got through the bismuth plug, we could see that the gas started to come. So this was a proof for us that the bismuth plug had been holding. We had seen no bubbles during those 2 years. We knew that the D annulus, as you can see out here, that's the D annulus, that had maintained 7 bars. 7 bars is about 100 psi. So there was no change to that. But when we drilled through and removed the bismuth plug, we started to see gas coming out again, and we can see the gas pressure increasing, while the pressure inside was actually more or less zero after it had been bled down. But the C annulus pressure, the red curve, is this annulus here that is empty on this drawing. That's where it started to leak. So that was proof for us that yes, indeed, the bismuth was working, but when we removed it, it stopped working. So this is again a thing that shows how we actually removed the tubing pressure. The tubing pressure was coming down and going to zero the whole time. The C annulus pressure was actually coming down each time we bled it off. It built up to a lower level, and eventually it became zero. And this is what happened in the video you just saw, that it takes some time to actually remove the gas that is captured within the cement matrix. So during those 2 years where we had the bismuth plug installed, we had did not have any pressure buildup in the main bore because we capped the top of the well and saw no buildup in pressure. No gas bubble had been seen downhole with downhole camera, and the fact that we then saw gas after we removed the bismuth was proof for us that indeed the bismuth was good when it was there, but the leaks came back when we had removed it. And as I said, the casing had shifted 3 inches, and that's why we couldn't get the plug with the gauge out, and that was a pity because the gauge hopefully had worked and we could have actually gone and downloaded the data, but now we couldn't. Again, we went through this qualification process, and we met the requirements, what we think we did. So 2 years, that was good proof in the pudding. And like Marcelo mentioned, bismuth material is impermeable, and we have done tests beforehand with other universities that actually showed that it was corrosive resistant as well. And it resisted CO2 and it resisted H2S. So all the tests that we did was talking in the favor of bismuth material. So after we had a successful test, after we had removed this bismuth plug after 2 years in the field, we decided that, okay, we're going to go for bismuth plugs in all the wells in the shallow waters, and well, basically 2 to 250 meters depth. And this picture is just to show the size of the bottom hole assembly. This person is 6 feet high or whatever, I'm not sure, but it basically shows the size of the bismuth material, which weighs 15 tons, as you can see it there. And we shipped it across the Atlantic Ocean, and as you can see, just handling this is it's handling a beast, more or less, and it weighs 15 tons. So it's not easily done, and well, it cost a bit of money as well. But anyway, we did that, and now I was going to go through a few pictures of telling you how we actually installed this. We had a few wells that we had, plugged according to, what we had normally done earlier, where we have placed an open hole to surface cement plug inside the 20-inch casing, surface casing, which is the normal thing. But we had not done anything to the D annulus. And the D annulus was leaking in, or actually bubbling a little bit in most of the wells. That's why we made the decision to seal all of them, because we were going to use this field center that this well is located at for many more years to come. So we wanted to make sure that we had done a good job. So we actually drilled out some of that cement to get deep enough and deep enough so we could log that we had decent cement on the outside. And then we actually made a section mill in the 20-inch out to the 30-inch, and then we scraped the inside of the 30-inch to make sure that we had removed anything that had to do with mud or spacer or old cement stuff that could potentially cause a leakage. So we made that window and didn't polish it, but we scraped it. So we had these small things that actually water viscosity flowing bismuth could actually crawl into and actually increase the frictional force, in addition to its expansional force that it also creates. So then we set a bridge plug on the inside to act as a base. We threw some sand on the bottom so we shouldn't melt the bismuth, so the bismuth material shouldn't melt the plug. And then we poured bismuth material in there. And then we monitored the bismuth plug for some time and saw that we got to zero pressure buildup. And after a year or so, we actually cut the casing because we had then gotten so good results on the D annulus that we could cut it. But we cut it actually in the middle of the sea. So the sea depth is about 70 meters here. And we cut the conductors, the surface casing and conductors at about 35 meters. So there's still a chimney of 30 meters standing up there. So we could go back and do ROV inspections later point in time. And we've done that yearly, and there are no bubbles. And now we are at the end of 2024. So this was definitely a success. And this is a picture of what made the difference for us. We started out with the green open hole to surface plug, as is normal, but we ended up with actually milling a window out to the 30-inch to cover the D annulus and all the inside of the 20-inch surface casing with one bismuth plug and its sealing. So that was basically my story. Back to you, Per.
Per, you are mute.
Sorry. Thank you, Martin. I must say you shocked me with, and I captured that. I'll quote you and get us started on a few questions, and maybe Catherine can comment on that. But you did say cement does indeed leak, which is we kind of know that. But my question would be, how would that cement which you showed on the video have looked like on logs?
That's the issue, that sometimes it depends a little bit on where the leak is. If the leak is out towards the outer casing, it's really hard to discover on a log. If the leak is between the inner casing and the cement, that's where the log is intended to show you the bond. So even though get a good log, unfortunately to say so, it's possible that it could leak like you saw.
Very good. So we've had a number of questions from the audience, and I'll open the floor to that. The first one was by Mohammed Mukhtar El-Trisi, who's asking, did you perform, and that's for Marcelo, I understand, did you perform any of these tests under delta P and temperatures to simulate the downhole conditions?
Yeah, so for the pressure, the pressure differential that we applied even surpassed, for example, the case that Aker BP had at Valhall. So we're confident that we tested a pressure range that is representative for the downhole conditions. And in terms of the temperature, I believe so as well. But our concern was not a particular bottom hole temperature. For a while, we were more concerned about like testing the whole temperature range for our particular alloy. So we tested from 20 degrees to 120. Not sure if you're gonna apply it at 120, but at least we know what's gonna happen with this particular one.
Very good. Then we had a question from Jovan Stoichkowski with the widths. In case of sustained annuli pressure, where we can have corroded pipe and settled mud and dirt, what successful rate can we estimate if we use bismuth plate? Maybe it's a question. Yeah, maybe it's a question for Martin also. You know, in the real application case.
Yeah, it's a good question, and it's a difficult question because it of course depends on how much if there is a hole corroded directly through the casing. If that's the scenario, then you will probably be best off to set the bismuth across there, or actually below this, if that's possible. If you set it below, then you'll stop, of course, the leak. If you set it above, it doesn't do you any good. So either across the leak or below, if possible. Yeah.
So Martin, for example, in these wells that you are sharing with us, how many of them did you plug with the bismuth, and did you observe any corrosion, any dirt, for example, to connect with this question? How was the state of the casing on those wells where you have placed bismuth?
This was inside. We placed it inside a conductor, so the conductor was actually in good shape. It was cemented. Some conductors had good cement, some had bad cement, but there was no corrosion that we discovered on the inside because this conductor was 1 inch wall thickness, so it was quite thick, and of course any corrosion would have likely, well, we didn't notice anything basically there.
And I think in response to the question by Jovan, based on what you showed and presented, Martin, if you create a very good window for placement of the plug by section milling, then you create the opportunity for success. If you were trying to place bismuth in an annulus through perforations, then you would need to make sure they're clean. You would need to make sure that annulus will receive the bismuth in better conditions. It might be more challenging for the application, which then calls into question the success rate.
I would think that we would not have any chance to clean the inside of the outer casing at that time. If we do perforations instead of section milling, it would be very, very difficult to prove that we have a clean inside of the outer casing. That's why we did section milling, such that we could open up an under-reamer and actually clean away the cement on the inside of the outer casing. The cement stuck to the wall. because if there was cement stuck to the wall across where we had the bismuth material, then that could be a leak path, a potential leak path. So that's why we section milled and did not perforate.
Very good. Maybe I'll ask Nina a question to keep the floor rolling. In your list of threats, Nina, you haven't listed seismicity and seismic events, which maybe doesn't get discussed so much in Norway, but in some other areas of the world becomes relevant for P&A programs. So between that and applying bismuth at higher temperatures, any comments?
I guess from my point of view, you have to remember working for the authorities or a regulator. I'm not very deeply involved in the kind of technical details of a specific qualification process. But I would like to say that when it comes to higher temperature, I think that's possible according to what I've heard from the bismuth vendors and what's ongoing in other parts of the world outside Norway. So definitively, what I also hear from vendors and operators here in Norway is that they look for potential qualification of bismuth alloy as a barrier towards deeper reservoirs and higher temperatures. But again, that need to kind of be proven and qualified. And when it comes to seismic events, I'm kind of curious what you actually mean by that. Also, do you mean more like kind of fractures or kind of unexpected events that could kind of make the well barrier element kind of to leak, or what are you actually thinking about?
Yeah, so the failure of barrier plugs that would have been deployed in wells at the time of P&A that could then be failed because of seismicity. So a shift in, the sudden arrival of pressures or fluids higher up in the hole because the plug failed. For which environment you can imagine then having a limited height perhaps makes the exposure a bit higher than if you placed 100 meters of cement.
Yeah, and then I would like to say, as a part of our well barrier philosophy or regime is based upon what we call safety factors and robustness. And we always ask the operator to consider, also you need to have some safety factors in your well barriers, and also to ensure that there are robustness. And that is the kind of good thing with cement, because we can pump a lot of cement as a 50 meter, 100 meter in the cross-sectional area, and it doesn't cost us too much. But again, when it comes to bismuth alloy, only use of 2 meters is definitively something else. And I have to say, I think that's why we emphasize this kind of risk and failure mode analysis, to make sure that if you're using bismuth, you need to make sure that the area you're positioning your well barrier in are clean and that it's a depth with integrity. So I guess for shallow gas, I think it's really a good solution, but for other kind of applications, it needs to be considered to kind of add up with other well barrier elements as well, probably. Okay.
Thank you.
Maybe I would like to also ask you, Nina. I really like the classification that you showed us that was done in the report, where we classified the bismuth plugs in 3 categories. And today, I think Marcelo showed us the one that melts inside the casing, and also Martin is showing us the one that you use. You are not melting the casing as part of the plug. So maybe I would like to ask you, how do you see the initiatives in the Norwegian sector regarding covering these three classifications, or are we more focused in one of those?
Yes, I think these three classifications are all about the deployment method and kind of the different vendors and their kind of prototype. As it looks like at the moment, I know that the one that is melted within the casing is the one that is kind of has been used so far, and that some operators look into that solution also globally. For the others, I know it's taken some time to get offshore, onshore, and test it out in a real well. And for the kind of full melting technology, there's been some testing, I know, in Canada on onshore wells, and I think that's really positive. But for the Norwegian continental shelf, we haven't heard about anyone that are planning to use it at the moment. So I think that's the status from my side there.
Thank you.
Before we go back, there's been a lot of questions for Martin on the practical applications, but I'll have one for Marcelo, just out of curiosity, well, actually two, but one is very quick. So you're showing the setup, your test setup with sand at the bottom of the tube where you're going to do the mechanical testing. So I'm curious, did you see the alloy completely filling up the sand, or does it get solidified in the sand and it doesn't reach the base?
So yeah, from what we have seen there, it was a colleague that was carrying out the test. So regarding the sand, that was also part of our learning process for doing the experiments, because at the beginning, like you are suggesting, yes, some of the bismuth was going into the sand, while it was still liquid. So then we had to change the sand for another one until we get some good compaction, that we were confident that, okay, there is no longer any bismuth seeping into the sand. But that also took some trial and error to get there. It sounds a simple setup, but it was very complicated to reproduce what you expect a downhole. So it took maybe 1 year just to get a working setup before we could actually measure meaningful results for the hydraulic push-out tests.
Okay, so then the follow-up question: if we place a bridge plug in a well, and maybe Martin, you have an opinion on that. If we place a bridge plug in a well and dump some sand on top of it before we put deploy the bismuth alloy for a more permanent solution, do we know what sand to place there to avoid the bismuth going to the sand, or is this a hit and miss at the moment?
Yeah, I guess I can answer that one. What we used on top of the plug was on top of the bridge plug was 2040 sand. We also need to remember that bismuth, being a eutectic alloy, basically, the temperature is such that if it goes, we used an alloy which is 138. So I saw that one of Marcelo's stamps on there was 137 or whatever. So that was probably pretty close to what we used though. Anyway, when you think about a candle, when it flows over, it solidifies pretty fast. And that's exactly how bismuth material also, or bismuth alloy actually also does. As soon as the temperature gets below its melting point, 138, it solidifies. And that's why it's so important, one, to take the heater out in time before it all solidifies, it cools down and solidifies. Because if it goes down by 1 or 2 degrees, it solidifies. And when it seeps through the sand, it actually cools down and solidifies. Also 138 degrees, which we used, shallow waters, is not hurting the material, any steel, because it's just too low a temperature. So there was no danger for that there. If you go deeper down in a well, things change. So that's why Nina said that we had to test it for warmer temperatures if we want to use it for warmer temperatures. But for us, it really didn't matter. Yeah, because it solidifies so fast. And I think we had roughly half a meter of 2040 sand on top of natural sand.
If I can, it's connected with this of the temperature melting. For cement, we have a clear classification, right? Cement class D, cement class G, cement class H. Have we any initiatives in Norway to try to do some sort of classification for bismuth, so that we can, let's say, talk about their properties as well, based on the alloy that we are using on the blocks? Or it's common that we are using 138 as a standard?
I'm not sure.
Should I?
Yeah. Go ahead.
Yeah, so the truth is that at this stage, many of the alloys being used are still proprietary. So we don't actually have their full compositions. And the one we are referencing here, the authentic bismuth tin, is kind of how everything started. So we said, okay, bismuth has this particular property, but pure bismuth is too, it doesn't have enough strength to hold. We tried the pure bismuth in the lab, and it couldn't hold any pressure. So we said, okay, the most basic alloy we could try is the authentic bismuth tin. And then we said, okay, if we go really deep and investigate this one, and we really qualify this one, it kind of extends by itself to any other alloy. You just need to follow the same procedure. But at this stage, the companies that hold this technology, they are trying different alloys with different melting points. So of course, then it depends on the application itself. It all comes down to the temperature where you want to set the plug, essentially. But so to answer the question, we actually don't have a way of rating that yet because of the proprietary characteristics. Yeah.
Good. So I'm showing Darren Wilkinson's question, which is a bit technical, and so Marcelo, if you want to comment or say we don't really fully understand that yet, it's perfectly fine. But over to you.
Yeah. So the thing is, I'm not the person most qualified to answer that one, because we have a material science in our team that would understand this mechanism better. And Darren knows her because he is familiar with our group here at NTNU. But what I can say is that we had some long-term tests. And I think the answer for his question was evaluated, but I think she hasn't published it yet. So I would suggest Darren to contact Andriani here at NTNU. He knows who she is, so I think she can give a better answer.
Stay tuned. Stay tuned for more information. Question from Gunnar. Yeah, so I'll show this one. No, sorry, Dwayne Noonan to you, Martin. Any theories to why the casing shifted?
No, one reason could be that the cement below there was bad. That's one possibility. And of course it could be also movements. Once you start, when we start milling the cement on the outside, and the nose of the bottom wall assembly is of course going inside that, below that window, it could be movements created by ourselves in making the window. That's one possibility. So if we by that actually causes damage to the cement, and that is a possibility. But we really don't know the exact reason for that. It can only be speculations.
Question for Nina.
It's regarding the TRL number 9.
So
that is,
regarding the TRL, the technology readiness levels, yeah.
So, yeah, regarding the track record of the application that needs to be proven. And that's this question of how can this be achieved for a battery which needs to last forever. So how many years of use, number of clocks, and monitoring is required to be qualified as 9?
Okay, yeah, no, I think that's a really good and very important question going forward with respect to qualification of all types of new technology, new solutions, and new value elements. And so what we have sketched out for the technology perforation cement on the Norwegian continental shelf is that there need to be a track record with at least 3 successful kind of deployments or installations of the new technology in a field that you have verified and monitored. And then you can ask us, how long do you need to monitor? But I think Martin mentioned that in his presentation with respect to long-term monitoring during the qualification test. So I think definitively a track record need to be based upon at least 3 successful tests, and that will then you can say it's field proven.
And we have used, of course, in Valhall and Hod these blocks, Martin, in both fields.
Yes, not all the fields, not all the wells on the Hod field. Some of the wells did not have any de-annulus pressure, but they were used. I can't remember how many wells it was used there, but it was used on all 30 wells on the Valhall DP platform. Yes.
And on that, I'll add my 2 cents as an engineer and say that very often the qualification trials are designed that we can then continue learning by deploying in the field. It doesn't mean, oh, if you meet these criteria, you're free to use it anywhere. It's more complex than that. So, and Nina is without, we don't want to put you on the grill, having to say, oh, these are the criteria, and then everything there is good. It's not like that. It's but the answer could be, it's a damn good program that is needed to qualify for eternity. Absolutely.
Absolutely. And I just want to add also, because someone asked me a similar question for some weeks ago on the plug-in abandonment seminar. And I think what we had to admit then is that so normally when you are qualifying new technology, you need to accept some failures, also trying and failing. And there is a process there, and you need to maybe plan for those trials or those failures in wells where you can monitor and where you can go back and repair. But definitively, as Martin has done, they have had a long-term monitoring plan, and according to my knowledge, they're also monitoring those wells and Valhall DP at the moment. So that's good.
Maybe I'll show a question from Gunnar Lende on the age of the cement that you showed us on screen, Martin. That should be fairly quick to answer.
The question is...
Can you see it? The cement? Go ahead.
Yeah, the question is about the cement that you show us leaking. How old was that cement?
Okay, yes. These wells were actually drilled in the early 80s. So they were 40 years old. So some, of course, were drilled through the 80s, so maybe between 35 and 40 years old. So it's quite old wells, to put it that way. And it was actually great because we had the opportunity to remove some of these joints that you saw was leaking there and give them to the Norse Research Center so they could do all sorts of tests on it. Because this was basically the first time they had the opportunity to look into wells that had been pulled out of the ground after having been sitting there for 35 to 40 years old. Yeah. So it gave a lot of opportunity for learning for many people, actually.
Yeah.
Exactly, but Martin, this is pretty relevant to the condition of many wells that will need to P&A in the future. Most of the wells will be of similar age or older.
Yeah.
I think that I can actually mention about my own experience, because I was one of the persons that worked quite a lot with one of these sections, and it was actually quite surprising in some publications as well about that. Quite surprising that this cement, the chemical characterization and the logs, it wasn't showing a very bad condition, and it wasn't, the cement itself didn't show a lot of degradation when you see the properties, the mechanical properties and the chemical properties. It was quite close to new cement, let's say. But it was clear based on the study that we did that was mostly the leakage paths that you have in the interfaces between the casing and the cement what was creating the integrity problems, and not the cement itself. So I think that that's also worth to mention, that that is more the leakage paths than the material itself.
Very good. I think I'll show one more question again from Darren, and I'll complement that with my own comments. It's really a question for all the panelists. And Darren's question is about is to know whether Aker BP is used exclusively low delta P bismuth plug for environmental plugs, or are you thinking, have you done any deployment or similar alloy for much higher delta P for primary, secondary barriers?
I will rephrase this question, is when we are going to see a deep barrier plug with bismuth in Norway. It is that something that is in the pipe, or I think that's the interpretation I give to this question, maybe.
And before we go into the answers, I'll tie that to a question I had from Marcelo. Being an engineer, do we think we are going to get tables or some sort of abacus with guidelines on the geometry of the plug, the delta P for isolation that we need, and the fluids in place that would help guide in the selection of bismuth alloy? So that's a general question for all the panel.
You want to start, Margie?
Yeah, our experience is basically with it's shallow grounds and low temperatures. So we haven't been deeper than 300 and some meters, and the pressure there has been hydrostatic. So that is our experience. When it comes to the fact, I think Marcelo actually showed one slide where they did a push-out test, and imagine that you can actually remove a little bit of, if you have a little bit of metal, like a donut, for example, around on the inside of a casing deeper down in the well. That and you melt bismuth material there. That 1 or 2 or 3 small rings that you make, donut rings, where you have a groove out into the metal, it would not surprise me that would increase the push-out force many times, because then you basically have to share the bismuth material in order to push it out. Now, whether we're going to go deeper or not, I don't know the answer to that, because we haven't tried it in Norway. But if we want to do that, we definitely need to do more research before we go into deeper wells. If we want it to be permanent barriers, if we want it to be a barrier during in a well that is under operation, that's a different story, because then we can do the permanent barriers at a later point in time. So I would definitely differ between those two things.
Marcelo, any comments?
So yeah, and regarding plug length, so this is something that we have been concerned with at the beginning of our research as well, because well, in our opinion, the capability of the bismuth alloys to reduce plug length is probably one of the best selling points of the technology. But if you don't qualify, then you go according to Norsoc, you would need to have at least like a bismuth plug that is equivalent to a cement plug in length. So then it's very important in this case to test and see how much we can reduce the plug length. So I believe that yes, we will be able to reach some number depending on the setting depth, temperature, and other characteristics. And I believe much of the lab tests and the numerical modeling that has been done can help with that, because then we can quickly check like several scenarios, as long as you have good quality data for the alloy characteristics, which in my opinion is what's missing nowadays. So, but with that, we would be good to go and simulate these scenarios and find out what's the ideal plug length according to the pressure differentials and requirements.
I see here there is a question for you, Marcelo, maybe connected with this topic, and it's the question is, at which temperature the creep occur in the bismuth, and if it's going to be a big challenge for deep plugs, or you don't see it as a barrier?
Yeah, so the problem with the low melting point in alloys is that the transition temperature for a metal to experience creep for the low melting point alloys, it's essentially something like below zero. So in practice, it means that any low melting point alloy is suffering creep at some degree. Which is something that you don't see for a steel, for example. For a steel to suffer creep, you have to be like above 400 degrees Celsius. That's why we use it everywhere in construction. And also that's why we use these low melting point alloys in other applications like soldering, because this kind of metals, they flow nicely when you melt them. So yeah, creep can be a problem for this alloy, essentially at any temperature. But the creep rates are very low for certain threshold temperature, as I discussed during the presentation. So then, yes, setting this plug in deep wells as the primary barrier is going to be a big challenge, unless we can, of course, use alloys that have higher melting points, or then have some of the components is more resistant to creep. So I see that there are other bismuth alloys that are being used and like ventilated around, and I suppose they would have like better creep characteristics in this sense. So there are other elements that you could add, like antimony or silver, in this sense.
All right, very good. So we've reached the 90 minutes that we had scheduled for the call, and for me, it's been a real pleasure to have you here today with us for our first webinar. Looks like we really should plan maybe for a follow-up session and show experience elsewhere with bismuth alloys, maybe land applications, hundreds of deployments that would probably shed a slightly different light, typical applications, etc. Catherine, any takeaways or final comments?
No, I think that I would like just to say thank you to the three speakers for your time and the opportunity to share this knowledge that you have been building in the last years. It has been years of work for all of you to come here to present. So just appreciate and the opportunity that we have to hear you.
Thank you very much.
Mm-hmm.
See you.
Have a good day. Bye.
Bye-bye.
Bye.
Bye.